Welcome everyone. In this video I'm going to show you the most common mistakes that people make before they fry their Arduino. So there are multiple fundamental issues that beginners overlook which causes them to destroy their microcontrollers. And actually most of these issues could be simply solved by reading the datasheet and the specifications, which is freely available on Arduino's website, but people don't do it. So I have done the homework for you and I will show you all the things that you should avoid in order to keep your Arduino safe and operable. So of course the main question is, how do you even fry the Arduino? And basically how you fry it is that you run too much current through it. And you can run too much current through it in several ways. So I will go through those ways and show you how it is happening and how you can avoid it. And in order to understand how you can run too much current through it, we should understand its power management. So that's why I have the schematics here, because I will show you how the current travels through different parts of the Arduino, and then we will be able to understand the issues. As you can see, this is an Arduino Uno's schematics. So some parts might be Arduino Uno specific, because other microcontrollers might have different parts on their printed circuit board, but the basic concepts are the same. So whenever it comes to overcurrent and heat dissipation and Ohm's law, that's same all over the world basically. So when it comes to powering the Arduino, there are like two basic ways, which are, let's say, the traditional or regular ways. The most straightforward way is here, and that is just simply the USB connection. And then the other is here, up here, which is the DC power jack. These connectors are on the front of the Arduino, they are next to each other, and they can be used to power the Arduino. So since we mainly use the Arduino with the USB cable, let me go through that first. So here the 5 volt comes in from the USB, and if you connect it to a USB 2.0 capable connector, then it can supply up to 500 milliamps. If you connect it to some more powerful charger or a USB 3.0 connector, it can happen that you are able to draw 900 or 1500 milliamps through this pin. But now let's just stay with the USB. So we have a maximum 500 milliamps, and then that first goes through this fuse here. And you can see that also the rating of this fuse is 500 milliamps. So actually, if anything which goes beyond this fuse, trying to pull more than 500 milliamps, the circuit would stop because the fuse would blow, and then the circuit is saved. And basically I could stop the video here, because one of the most common cases is that people blow this fuse. If you browse Reddit, it's infested with these things. You can find several questions related to this kind of topics. And then people often upload pictures where you can see that it's just they destroyed the fuse. But then the reasons are a bit more critical here, so I'm actually going to dive deep in the issues and the causes. So okay, let's say that we didn't trip this fuse, so we can continue our path towards the USB VCC, which actually ends up here. So we still have our 5 volts here, and then we encounter this P-channel MOSFET. And to understand how this works is quite fun. So let me name the pins so I can explain them more properly. So here we have the drain, and then here we have the gate, and here we have the source. So then what happens is that by default, when only the USB is connected and there is no gate voltage here, this thing is off. Then 5 volt comes here and it drops through this body diode. So then actually the VS here will be, let's say, roughly 4.2 volts. Why? Because there is a voltage drop to this diode, and that is, according to the datasheet, is around 0.8 volts. So let's say that this will be our voltage here. And then here the VG is still 0 volts. So in order to turn on such a MOSFET, there is a VGS threshold voltage, which means that the voltage difference between the gate and the source should be more negative than that number. And that number is again defined in the datasheet of this specific MOSFET. And the datasheet says that actually this voltage should be below minus 1.5 volts. So how to determine if we are below that is that simply we calculate this. So VGS is VG minus VS. I guess you could guess this yourself. So that is 0 minus 4.2, which is minus 4.2 volts. And that is obviously smaller than minus 1.5. So actually, when the 4.2 volt appears here, then the MOSFET will turn on. And that will also mean that now actually this will be different, because since the MOSFET is on, then this whole thing crosses the MOSFET instead of the body diode only. And then here the source voltage will be 5. So eventually this becomes minus 5 in that case. But yeah, business is done here at the source. And then the USB directly feeds the global plus 5 volt rail. So everywhere where you see this plus 5 and this upward arrow, for example here, that is connected to the USB voltage. And then if we go back to the fuse, then whatever is connected to this 5 volt rail, including this 3.3 volt voltage regulator, that is like the current is crossing this fuse. And the sum of the currents, which are like here, cannot cross 500 milliamps. First, because of the fuse, and second, the USB, if it's a 2.0 connection, cannot provide more than 500 milliamps. And actually, that is not exactly 500 milliamps, but more like 450, because we have the Arduino here and other objects on this printed circuit board, which roughly consume 50 milliamps. So then you can only, let's say, manage with the rest. So you have 450 milliamps roughly to deal with. But then we also have another power source, which I briefly mentioned previously, and that is this DC jack. So if you connect your wall adapter to this DC jack, then Arduino recommends that this should be between 7 to 12 volts maximum. And then the power comes in, goes through this diode, and then it goes in this 5.5 volt low dropout voltage regulator. Again, we can look up the datasheet of this thing and we can have a few interesting details. First of all, this can actually source 800 milliamps, and it has a 1 volt drop, and its maximum voltage is 20 volts. These are interesting to keep in mind because of the following thing. So first of all, if we power this with a proper power supply, let's say a 9 volt and 1 amp power supply, then on the right side, so at the output, this power regulator or voltage regulator will be able to output 800 milliamps on this 5 volt rail, which is again all over the place. This is the global 5 volt rail. So instead of 500 milliamps, now we can actually consume 800 milliamps, or 800 milliamps minus 50 milliamps, so 750 from the 5 volt pin. And also another interesting thing is that this thing, so we discussed this, I just struck it through, we have a 1 volt drop. That means that the VI minus the VO is, it can be 1 volt. So that means that if you calculate backwards, is that 5 volt plus 1 is 6. So if you actually put 6 volts here, then the output will be 5 volts on this side. But the recommended voltage is 7 volts. And we will get there why. It's a very smart thing why it is 7 volts. But we just have to keep in mind that actually the voltage regulator can already provide 5 volts when you provide 6 volts to its input. And then again, it has 20 volt maximum input voltage, so actually here you could feed it with 20 volts. But there is a problem. How a voltage regulator, this kind of voltage regulator works is that whatever the difference of voltage between the input voltage and the output voltage times the current on the output pin is turned into heat. So actually the difference is just dissipated as heat. So if you have this formula, then if you substitute the numbers, then 20 minus 5, and let's say we consume 500 milliamps, then actually this becomes 7.5 watts. So that's a huge amount of heat to get rid of by that small piece of chip. So another reason why you can kind of burn your Arduino is that you burn this chip by providing too high voltage to it. So some people neglect this 12 volts, let's say, and then they provide, I don't know, 20 volts, and then it just breaks down. So actually what I would recommend is to use a 9 volt power supply. So let's say a 9 volt and 1000 milliamps, because then you only have to have, let's say the delta is only just 4 volts, and you draw, let's say 500 milliamps again on the 5 volt rail. So then that is 500. So basically that is quote unquote 2 watts of power. So that's almost 4 times less than the 7.5. So less chance to break your voltage regulator due to overheating, and then you also waste less power, because whatever is let's say dissipated as a heat, that is just wasted power. Very bad efficiency. And then I mentioned that this 7 volt has a funny interpretation, and that has something to do with the MOSFET here. So I told you that by default, and now let's put this experiment back to the default state when we have the USB plugged in only, the gate voltage is 0 volt. So this guy here. And why it is 0 volts? It is because here we have 0 volt on the output of this op amp. And how do we generate 0 volts there? So let's go to the V-in. So the V-in is the voltage which comes out from the DC jack. You can see another flag here. And that V-in first goes through a voltage divider, which has equal 10k resistors. So that means that here, whatever output voltage will be, is actually V-in divided by 2. And therefore, if you provide 7 volts here, then it will be 3.5 volts here. And if the input voltage on the non-inverting input, the positive pin here, is larger than the input voltage on the inverting input, which is 3.3 volts here, the op amp will turn on. So actually then the voltage is 5 volts here. And then actually the gate voltage here becomes 5 volts. And therefore, if we recalculate this formula, let's call it VGS prime, then that is 5 minus 5, which is 0. And in that case, we don't reach the threshold voltage, because then what we have here is the threshold voltage should be at least less than minus 0.4 volts. But we are beyond, well beyond that. So then what happens is that the MOSFET turns off. And then that will automatically select the power supply as the DC jack, or more precisely as this 5 volt low dropout regulator. So that's that. And this also means that you can have both the DC jack and the USB plugged in your Arduino without damaging your USB port on your computer, because then the USB connection will be only used for communication, and the power will be provided from this power jack and the 5 volt regulator for the rest of the circuit. And actually there are some more adventurous ways to power the Arduino. On the board itself there is a pin called V-in, so it's actually that is this V-in here. And what you can see here is that it skips this diode, so there won't be, let's say, reverse polarity protection, and it goes directly to the voltage regulator. So actually it has exactly the same purpose, the V-in. It's just that you should be very careful about the wires, how you connect it. And then also you can just take the 5 volt pin on the Arduino, which is like there on the board, and you can connect an external 5 volt power supply to it. But then the problem is that we basically circumvented all the possible protections which we could have. So in this case, it's not really recommended to have the USB and this external power supply of 5 volt connected to the circuit. So either you use the USB or use the external power supply, but not both at the same time. So now we roughly know how this thing works, and I want to show you through some specific examples I see on the internet how people mess their stuff up. And one of the most typical thing is to use this SG90 servo motor. At the top I have the wrong example, and I tell you why this is wrong example. So if you look up the specifications, and again you just have to read the datasheet, then you can see that actually this is rated to 4.8 up to 6 volts. So that's fine, you can drive it with 5 volts. But it also says that it can consume up to 500 milliamps. And you can already see that what we discussed a few minutes ago is that actually you can only draw 450 milliamps roughly from the 5 volt pin. Otherwise you will draw too much current and you will trip the fuse on the Arduino board. And actually this is one of the connections how the let's say beginners try to drive their servo motors, sometimes motors, so it's really plural, that they just simply power it from the 5 volt of the Arduino because they don't look beyond the specifications other than the voltage, and then they try to drive it. And then what happens is that, let's say there is a load on the servo, so it will try to actually draw this half amps of current. And then what happens is that that 500 milliamps will trip the fuse somewhere here, and then the fuse will blow. And in a good case, since these are some polymer-based resettable fuses, they will just cool down and will be usable again. But if you sustain the current through them too much and they don't act as they should, they might burn. Their resistance should increase with increasing current, so that is actually how they cut off the current. But this doesn't mean that they cannot burn out. There are examples on the internet of this. So this is a very wrong example on the top. So it should not be used as this, and this is one of the most typical mistakes that people do. And then the correct drawing is right here. So I just illustrated the external power supply with an additional jack here. And I just say that, okay, I connect a 5 volt 1000 milliamps power supply. And what you should see is that we have the positive pin here, and then the positive pin goes to the positive pin of the servo motor. Plus, as I said, this is a more adventurous powering of the Arduino. But let's imagine that now we are not connected to the Arduino by USB. We are running it in standalone mode, just the board itself, and then we can actually power the Arduino here with the external power supply, but we just have to be careful. So that's that. And then the negative, the minus pin, also from the power supply goes to the servo, and this is also a typical mistake, it has to go to the ground of the circuit here. Why? Because, for example, you have the signal coming out here, and now you just imagine as water. So the water can only flow, in this case, just one direction because of the, let's say, pipe. So then actually the signal from the PWM pin goes into the servo. But it also has to return to the microcontroller some way to actually create a so-called circuit. That's the whole point of building an electrical circuit. The path has to be closed to have conduction. So then, if you neglect this black wire, so the ground between the Arduino and the power supply here, then you cannot drive the servo. And the same also applies, so this ground actually has double purpose, is that if you only run the positive pin to the Arduino from the external power supply, again, the positive, let's say, flow goes into the microcontroller, but it doesn't find its way back to the wall socket, and that's not too good. So then again, that would cause some conflicts, and the circuit would not work. And one more remark here. You could say that you don't use this at all because you plug in here in the DC jack your, let's say, 9 volt and 1000 milliamp power supply. And as I said, actually this LDO would be capable of giving 800 milliamps. So why not power the servo directly from the 5 volt power supply here, or power supply pin, if I can supply 800 milliamps because of the external power jack. And yes, that's absolutely correct. You could do that, but it's just not recommended because, again, you drop some voltage here, 4 volts, and now you run 550 milliamps at least, 500 because of the motor when it's at its peak, and 50 milliamps from the Arduino at least. So then that is already more than 2 watts of heat appearing on the voltage regulator. So it's possible, but I would avoid it. I would just use an external power supply and then let the Arduino do its stuff as it should. And then I would avoid connecting, let's say, multiple things on the 5 volt rail. And then there is another fun stuff here, which I saw on the internet, and I want to explain you this. Quite similar to the previous scenario, so again we are just trying to drive a motor, but I saw some extreme examples which leads us to another set of problems that I can explain here. So you can see that I even used some, let's say, extreme expression like extremely wrong, because this is really extremely wrong. So what happens here is that people think that the GPIO pins here can source a lot of power, because again they did not read the datasheet, and they think, oh okay, I can switch the GPIO pin on and off by using the digital write function, so why not put the motor on this, because then essentially it's just a switch, the microcontroller is a switch, and then create this circuit which is up here. And that is actually super wrong, because what would happen is that as much current as the circuit allows could drive or go through this motor. And why is this bad is because of the following. If you look up the datasheet, then depending on how you interpret it, but it says that anything between 20 to 40 milliamps, which you can source, so source, let's use this arrow in this direction, from a GPIO pin. The GPIO pin physically could source more, but this is what it can sustain. But a motor can draw much more current, especially when you start it. There is a peak to make it spin. And I have a motor here, similar than on this illustration, and I tested it. And when I start it, then it peaks beyond 100 milliamps. So let's say I peak and I just write it like this. And when it's running without load, so let's say normal, that is roughly 70 milliamps, a little bit below that. And if I load it, then it is several hundred milliamps. So I just write 200 or 300 milliamps. So then in that case, if you have a loaded motor on this GPIO pin, then it would draw like 10 times the current that you're supposed to draw maximum from the GPIO pin. And even 200-300 milliamps, that is not enough current to trigger the onboard fuse, which is somewhere here. So then eventually your Arduino chip will burn out because too much current will try to flow through the GPIO pin. So this is a very huge violation of one of the basic rules of how to use a GPIO pin. And if this would not be enough, let's say 200 to 300 milliamps is the current draws of this motor under load, then actually the datasheet also says that the total amount of current through, let's say, all the GPIO pins simultaneously should not be more than 200 milliamps. And that also like leads us to another problem, is that including me, people sometimes switch LEDs with this configuration. So let's say you have a resistor here, and then LED, and then this will go to the ground connection of the Arduino. And then if you have more of this, then you can actually violate the other rule, which says that across all of these I/O pins, you can only take up 200 milliamps. So what I try to say is that, yeah, you can run a few LEDs, but always respect this rule. But try to avoid too much high power LEDs on the GPIO pins. Don't drive them with the GPIO pins. Use a MOSFET to switch a higher power source to switch on LED. And kind of the same rule applies backwards. So you can say that, okay, I switch one of my I/O pin to low, so this can actually, let's say, sink current. So I could do something like this. So here we have the LED, and then here we have the resistor. But actually it can also sink very small amount of current, so you can destroy the Arduino this way as well. So don't do that either. So yeah, this is a super extreme example, and it should be avoided. And then below that is, let's say, the correct example, that you have a external power supply, which is in this case 12 volts and 1000 milliamps, because let's say that's the rating of the motor. And then I have a dedicated motor driver. And this is not only good because it protects your Arduino, but it allows you to control the speed and the direction of the motor as well. And you can see here that we have the 5 volt pin connected, but that is not the power pin in this case. It just provides 5 volt as the logic voltage to this controller, and that's all. It will not draw too much power here, so that is now a different type of 5 volts. And I actually have a third thing that just came to my mind, and I did not draw it here, but I can explain, is that sometimes people think that, oh, okay, I can just, let's say, cut this wire, and I switch a MOSFET or a relay, and that MOSFET or relay will drive this, but then they make the mistake that the input of the MOSFET or the relay will be still connected to the 5 volt. But then that doesn't, let's say, destroy the Arduino through the GPIO pins, but it will probably destroy the fuse, because again, it could be that they connect a high power rated motor to it. So actually through the 5 volt pin, they can draw the 500 or 800 milliamps. Whatever power source is connected, either the USB or the DC jack, and then yeah, that will either blow up the fuse or the voltage regulator sooner or later, or will damage it. So don't do that either. Use an external dedicated power supply, as I showed it in the example. And just in general, just don't put any high loads on the 5 volt pin, and especially not on the 3.3 volt pin, because the voltage regulator for that pin can supply even less current than the 5 volt voltage regulator. So to summarize everything, I have a few points to tell. So first, create a power budget. What that means is that you look up all the components that you want to use and check their current consumption, sum it up, and then check if the sum of all of your components is less than, let's say, 450 if you power from USB, or 750 if you power from external power supply using the DC barrel jack. And then if you are below it, below this threshold, then you are safe to use the 5 volt pin. Otherwise, use a dedicated external power supply for the 5 volt components. For example, if you use too many displays, big LEDs or sensors or modules, then you might want to use an external power supply for them. Then also, I already mentioned that it's a huge violation that people try to power things from the GPIO pin. A few LEDs, yeah, it's fine, but respect the rule of the 20 milliamps, don't consume more. So for example, if you have a regular LED LED, do not use any resistor below 250 ohms. And how that comes is that if you have 5 volt and you divided it by 250 ohm, then that consequently becomes 20 milliamps. So it's just borderline. And even though I made this calculation and it is borderline, that is actually already with a safety margin. And why? Because in reality, you should subtract the forward voltage of the diode from this 5 volt, and for a red LED is typically 1.6 volts. So actually you can do this. And to reach 20 milliamps, you need a 170 ohm resistor. So that is also 20 milliamps. So actually if you use this, but then you have the forward voltage, then actually the real current here is only 13.6 milliamps, and that is kind of safe. And then also if you drive a DC motor or a stepper motor or any kind of motor, use a dedicated motor driver, because yeah, as I said, they also allow you to regulate the speed and the direction, and they protect your Arduino. And then also never forget about the ground connection. So you can see that here the ground comes in from the external power supply, and that is actually shared across all the grounds on this specific board. And then I have one of the ground pins connected to the ground of the Arduino. So the signals and everything has a return path to the Arduino. It's very important, otherwise you might not be able to use the driver at all. And finally, maybe that's maybe too obvious, but people can overlook it. Always double check the polarity of everything. For example, if you use these DC barrel jack based power supplies, some of the wall adapters have the negative pin in the center and the others have the positive in the center. So make sure that you know which kind of power supply you use. And also, especially when you are moving along these pins or around these pins, you can see that the 5 volt is next to the ground and the V in is also next to the ground. And if you accidentally short them or mix them, then that could have catastrophic consequences. So basically this is all. And I'm planning to run a series of these kind of, let's say, common mistakes with Arduino and so on, based on what I read on the internet and what I see on the internet, or what I encounter myself, because obviously I did like thousands of mistakes myself as well. So I will try to compile all these things into a video series, and we can consider this video as the first in that series. If you want to have more information, please visit my website, because I wrote a very detailed article there. So check the link in the description and check what I wrote there. And also, if you like this series and want to contribute, please consider supporting me on Patreon. Link is in the description again. And obviously don't forget to subscribe. And if you have any remarks, please leave a comment in the comment section. So I hope this video was useful to you. I hope you learned something, and see you in the next video.